Okay, so I'm making this video. It's not a live stream, because originally I was live streaming, um, going through this paper, but apparently my internet cut out sometime during the live stream. I didn't notice, so I actually completed the first paper of the methods, sample paper, and after paper one, I just checked to see if everything was all right, but it wasn't. So I have actually attempted every question, and when I thought I was live streaming, I went over the marking scheme and I marked everything. So in this video, I'll just be discussing the strategies and the different things we need to be aware of for each question. But I'll try and make this short because I've already written everything. I've already done the questions. So I'm just going to explain the solutions. So I have the screen. So I have exam insights on the bottom left to show the marking guide and the questions for the multiple choice. And then I'm obviously also have this. Now, if I want to explain the questions just a bit more in detail, I'll use this notebook. Okay, this video will only cover the first paper for this method sample, but I'll make another video a bit later about paper 2 because I don't trust my internet connectivity, and also like the video quality in my streams are not great. They're not great. So I think maybe like tomorrow I might stream after I tutor, but yeah, it depends. It depends. Okay, so question 1. The random variable x is binomially distributed with 10 trials, so n equals 10, and it's a discrete random variable, and a probability of success equal to 0.25. So this is tech free as well. So p equals 1 over 4. Value of the probability of getting x is greater than or equal to 1 is equivalent to, and then we get 4 different options. Okay. Immediately, what we should be thinking is we don't want to calculate the probability of getting 1 and the probability of getting 2 up to 10, right? That will be very time consuming. It will probably be correct, but we want to be efficient in an exam. We do not want to be spending more than 5 minutes, 6 minutes on one multiple choice question. That is not ideal. Okay. Ideally, 1.5 minutes per mark. That's kind of the aim. If we get faster than that, that's excellent. We have more time at the end. If we spend, less than 1.5 minutes per mark on average throughout the whole paper, we have more time to spend on double checking, triple checking, and quadruple checking our work. Okay, so here, I believe the multiple choice was, I did show the multiple choice in the stream, but I'll just be going over it in case you haven't seen that. And also, you can actually properly see what I'm doing. Okay, so this is the probability given. Yeah, the probability that x is greater than or equal to 1. And we know that we can get the complement, but we need to do 1 minus the complement. Because it's like saying we have a graph. Yeah. It's not normally distributed, but let's say we have a graph that's normally distributed. we have this point here, yeah. We want the probability of this, but we have, let's say we're given the probability of the values before that point. So less than. To get the probability that's greater than, we go 1, which is the entire graph, minus this to get this part. Same thing here. So we're basically going 1 minus the probability that x is less than 1. So it can't be equal to 1, and it can't be greater than 1, so it must be less than 1. That means that only leaves x is greater than 0, x is equal to 0, since it can't be negative, and we know that it's a discrete variable. So it can only be in terms of integers. So it's 1 minus that, and then we're using our binomial, the binomial like formula. So we have, let me show it. So we have here, okay, the binomial probability. So then we have when the probability that x is equal to r equals, so the combination. So the number of trials, we're using combinatorics here. So n represents the number of trials, r is how many successes we achieve. And that's multiplied by the probability of success to the power of r, and then 1 minus the probability of success to the power of n minus r. Okay. So using this, we can get, so the probability of choosing 0 in n trials is just 1. There's only one way to do that. So the coefficient is just 1, so we ignore it. How many times are we getting a success? 0 times. So p to the power of r is 1, because r is 0 in this case. 1 over 4 to the power of 0 is just 1. So then that's why it's 1 minus, I scribbled this out because it's just 1. And then it's the complement, so 1 minus 1 over 4, which is 3 over 4. And that's to the power of the number of trials, which was 10. So it's 1 minus 3/4 all to the power of 10. Okay. Now let's see. Let's navigate over here and see if there is an answer like that, which there is. It's D. So we pick D. It is D. Okay, question 2. The approximate area under the curve y equals 2x squared between x equals 1 and x equals 4 is found using rectangles with 1, as shown in the diagram. What is the approximate area found using these rectangles? Okay. So the width is 1. Okay. If the width is 1, that means the height is actually the area, right? We're just timesing the width, which is 1, multiplied by the height. So overall, the height is representing the area. Okay. So here, I actually did that. So we just sub in the bounds. We can see that in the rectangle, or in the diagrams, the right corner, the top right corner determines the height of the rectangle. So it's the value on the function that is the same. Well, no. In the intervals, it's the right value that determines the height of the rectangle. So for example, to find the area of the first rectangle, we just find the y value, the height of the rectangle at x equals 2, because it coincides with the vertex of the rectangle coincides with the point on the function. So then when we sub x equals 2 into 2x squared, we get 2 cubed, which is y equals 8. So that's the area of the first rectangle. Same thing, we just go to x equals 3, and we sub it in. So 2 times 3 squared is 2 times 9, which is 18. 32, again, we sub in x equals 4. So 2 times 4 squared equals 2 times 16, which is 32. When we add these two together, we get 50. So then it's 58 when we add 8 to that. So then 58, it's A. Here we have another pretty quick question. So we're deriving cos of 3x all squared. The entire thing is squared. So we're going to do the cosine. We're going to derive the cosine part. We're also going to derive 3x, and we're going to derive the entire square part. Okay, so we're like applying the chain rule twice. First, we derive the inside of the bracket. So it's 3, because 3x becomes 3, right? We just take the coefficient. When we derive cos, we get negative sign. So we get negative sign, and then whatever's inside the brackets stays the same, so it's 3x. Then we have the square to derive. So we just ignore what's inside. So it's like, let's say u is cosine of 3x. So u squared becomes 2u when we derive it. So it's just 2. The coefficient is negative 6. So we actually don't need to worry too much about anything else. So it's just A, because that's the only one with negative 6 at the front. Okay, question 4, which of the following is true? So we're given that the integral of f of x from negative 2 to 0 is 4, and then from 0 to 3 is negative 10. So if we were to draw that, it would be like, we don't know the function of f of x, but it's from negative 2 to 0 to 3, right? The area in here is 4. The area between 0 to 3 is negative 10. Because of that, when we go from negative 2 to 3, we're just adding this, so it's negative 6. Okay. And all the integrals are asking for the integral from negative 2 to 3. And we've determined that the value of the integral would be negative 6. So in this case, it's B. Slope of a tangent at y equals ln of x squared at x equals e squared. Okay, so here I've done the question. Yep, we're deriving it. So chain rule, when we derive the inside, so x squared goes to 2x, and then we're multiplying by the derivative of ln. So it's 1 over whatever's inside the brackets, which is x squared. The x's cancel, leaving us with 1x in the denominator, so it's 2 over x. Okay, then we sub in the x value at the point, or at x equals e squared, so it's 2 over e squared. That's the derivative at x equals e squared, and therefore it's also the slope of the tangent at x equals e squared. Okay, so then we get a value of 2 over e squared, which is b. Yeah. Okay, integral question. So the bounds are from negative 1 to 7, and then we're integrating 1 over square root of 2 plus x. We can use our substitution. So u substitution. We let whatever's inside the square root equal u. Now, the reason why that's important is because if we were to derive this, it goes to 1. The derivative goes to 1, so there's no x value, which means we don't have to deal with multiple variables. If we were to let the square root equal u, then we'd be dealing with a bracket with x. But I'm pretty sure it would still be allowed. Let's try that. Let's try that. If u equals square root of this, the square root, du dx equals to the derivative of the inside is just 1. Then this is equivalent to saying it's just raised to the power of a half. So we put the power at the front, and then we minus 1 from the power. This is essentially 1 over 2 multiplied by 1 over 2 plus x raised to the half, right? Which is essentially saying 1 over 2 multiplied by 1 over u, because we know u, we let u as this, 2 plus x to the power of a half, and then we're just subbing the u back in. And this should actually still work. If we rearrange for d of x, and then sub it back into the formula. Because we know that if we were to do that, so in this case, it's 1 over 2u. So to isolate, to move 2u, we just multiply it to both sides. So it's 2u, and then that equals dx. Then when we okay, you know what? I might use the other one. So when we're integrating, these bounds are in terms of x, but we're still writing them because we're going to sub in the u value back in. Okay, so it was 1 over u. And then dx equals 2u. 2u du. Okay, this is a bit strange. This is a bit unusual, yeah. Interesting. Anyways, the u's cancel. But I don't think that means it's wrong. In this case, it becomes 7, negative 1. We can factor out the u, not the u, the 2 out the front. That leaves us 1 with 1 du. These are in terms of x. That's something to consider. So when we integrate it, it's a definite integral. So this becomes u. But then these bounds we do not sub in as u. We need to sub what u was, which is square root of 2 plus x. Yeah. And so we factored out 2. And here we sub in the values for x because these bounds are in terms of x. So 2 plus 7 is 9. Square root of 9 is 3. Minus square root 2 minus 1 is 1. This becomes 2 minus 1, which is, 3 minus 1, which is 2, and then 2 times 2 is 4, which I believe is the value we got. Okay, so regardless of whether you sub it, whether you sub u as the square root or whatever's inside the brackets, it will actually work out, which is good. Good news. Okay. So what I did was, in this case, I let u equals 2 plus x. Then I derived it, which meant that du just equals dx because du dx was 1. And then I made the bounds in terms of, I turned the bounds in terms of u. So then I subbed in the x bounds into what I let u, and then I got the u values. So 2 plus 7 was 9, 2 minus 1 was 1. So then now I, I subbed in the values of the variable of u into the integral, and then I subbed in du, which was just equivalent to dx. And then this, if you turn it to exponential form, it becomes u to the power of -1/2, because negative is from it being the reciprocal, and half is being from the square root. Then I just integrated this with definite integral, and then we got 4. All right, same process. Okay, it's D. Yep. Distribution in 3 subjects is given below. The mark received by a student in each of the subjects is also shown. Standardized z-scores were used to compare the results and show that the student. Okay. In this case, we can use z-scores. So I calculated the z-score of science. So x in this case was the student's mark, which was 70. We subtract by the mean, which is represented as mu, which was 60. So 70 minus 60 is 10. And then we divided by the standard deviation of the data, which was 15. So 10 over 15 simplifies down to 2 over 3. Then I determined the z-score for math. Same thing, student mark was x, the x value, so 72. Then we subtract mean, which was 68 for the math test. That becomes 4. Then we divide by the standard deviation, which was 6, so it's 4 over 6, which simplifies down to 2 over 3. These are equivalent. Okay, so math and science, they performed equally well in math and science. Okay, so that means it's A. We don't need to proceed. Okay, we've found that z-scores are equivalent in this. Okay, question 8. Given y equals 5 e to negative, not negative, 2x, rearrange the function to make x the subject. Okay, so immediately we should be thinking there's a constant at the front, right? The coefficient out the front, we divide by the coefficient. So y, we have this. So this is the first line of working. We divide by 5 on both sides to get y over 5. And then we have e to the 2x. Then I did the natural log on both sides, right? Then we use our log laws to get the power inside the brackets and move it to the front as a coefficient. So then it becomes 2x out the front and times ln of e. ln of e is 1 because the base is equal to whatever's inside the brackets. Then it becomes ln of y over 5 equals 2x. Then to get x, I divided it by 2. Okay? However, you can notice that none of the answers are expressed like that. None of the answers are half multiplied by ln of y over 5. They have square roots. Now we can do the reverse of the log law we applied for this, and instead use the coefficient and make it into the power of whatever's inside the brackets. Earlier I said how the power, when you convert square root into a power, it's 1/2. Same thing here. So we actually square root whatever's inside the brackets. So we get x equals ln of square root of y over 5, which is A. An equilateral triangle has side lengths of 9 meters. Equilateral triangle, side lengths are all equal. The angles are all 60 degrees. They're all equal. Okay. The area of the triangle is what? Okay. Here, we can navigate up here because my working out was up here. So this is from the formula sheet. A equals a half BC sine of capital A. BC, lowercase, represents the side lengths in the triangle. Capital A represents the angle that's opposite to side lowercase a, which in this case was not included in the formula. Since B and C are going to be equal, they're both 9 meters, because it's an equilateral triangle, we just go 9 times 9, and this is divided by 2 because of the half. Okay, sine of 60 degrees, any angle in the equilateral triangle is going to be 60 degrees. We can go over here, we go from our exact value table, which we can get using the method I said in the stream, easy as 1, 2, 3. So we go 1, 2, 3 for sine. Square them. So square as in like square root. Square root of 1 is just 1. Square root of 2 is that. And then just apply the square root sign. And then square them, halve them. So then now you just halve them. So then from 30 degrees, 45 degrees to 60 degrees, it goes half square root of 2 over 2 and square root 3 over 2. Right? And we're dealing with 60 degrees, which is pi over 3. The sine of 60 degrees is square root 3 over 2. And that's multiplied with 81 over 2. The denominator goes to 4, and then the coefficients just, the numerators just, you just combine together. So 81 square root 3 over 4. In this case, it's safe. Perhaps an easier way to, a quicker way to do this question in an exam is think about the formula, think about how angles are used, right? And then work out the angle, because we know that this was sine of 60 degrees. Sine of 60 degrees is square root 3 over 2. There's only one answer that has that. So, yeah, you can work it out that way. Okay, if the sample size decreased, but the sample proportion and the confidence level remain the same, the width of the confidence interval. Okay, here we have the margin of error, which is representing the width of the confidence interval, and it's equal to z square root of the population proportion, estimated sample proportion, I think, and then multiplied by 1 minus p brackets divided by n. Okay, so they said if the level of the confidence interval, right, equals the same, it's maintained, right? So z depends on the confidence level. So this is going to equal the same. It's going to be the same. Okay, and then the sample proportion is going to be the same. So these values won't change it, but n decreases. If you divide something by a smaller number, you get a bigger number, right? So if I divide 50 by 2, I get 25. But if I divide it, well, if I originally divide 50 with 100, I get a small number. But if I decrease what I'm dividing it by, I get a large number. So if I decrease n, I'm going to get an increased number, right? If I have a cake and I divide it by 4 pieces, right? I cut it twice. I get 4 pieces. But if I cut it into very small pieces, right, the amount I'm dividing it by decreases a lot. I get many pieces, right? I get like, let's just say 100, I don't know. So it's more. So the width, the margin of error of the confidence interval will increase. So it's A. Let's go over these questions quickly. So I'll just have the exam insights part open. So in this case, 1 mark. It's just for getting 3 over x. What we did, chain rule. So the coefficient, right, the constant out the front just stays there. And then we multiply by the derivative of the brackets, which is 5. When we derive 5x, the power of x comes to the front as a coefficient, which is just 1. And then we subtract 1 from the power, so x to the power of 0 is 1. Then we derive ln. So we pretend the brackets is just one term, which it is. Then we just go 1 over that term, which is 5x. The 5's cancel, giving us with 3 over x. Okay. This involves the product rule. We have two functions, we're multiplying together and we're deriving them. So then the marking guide for this is you get 1 mark for demonstrating that you need to use the product rule. It might be implied. They might allow implied working, but either way, it's probably always best to just demonstrate that you know which rule you're using. Like you can probably write down product rule, just in case in an exam. So by writing this, I demonstrated that I'm using the product rule. Okay. And then u in this case was x cubed, and then v was cosine of x to the power 4 plus 1. Then I derived u, which was we bring 3 to the front, so 3, and then we minus 1 from 3, so x squared. Then we just leave v, so cosine of x to the power 4 plus 1. Then we add u, so x cubed, and then we derive this, so the chain rule. So we derive what's in the brackets, so the constant just disappears basically. And the derivative of that goes to 0. We're just focusing on x to the power 4. So bring the 4 to the front, and then subtract 1 from 4 as the power. So then when we bring 4 to the front, it's just 4 multiplied by x to the power of 3, right? And then we multiply by the derivative of cosine, which is negative sine, and then what's in the brackets is just kept. Okay. And it specifies you don't need to simplify, so that is full. You're awarded full marks for that. We're integrating them. E to the x, so exponential functions, are pretty easy to integrate because the integral of them is just the same. But since we're dealing with the chain rule, we do have to divide by the derivative of the power, which is 4 in this case. We leave the constant, we multiply by what it was, and then we divide by 4. So that's our answer. Okay, so then here we're applying log laws. So this has a coefficient of 2, so we put that as a power, so that becomes 2 squared, which is 4. They both have the same base. These two logs have the same base. So we can actually apply our log law and multiply what's in the brackets together. So 9 times 4 is 36, so it becomes log base 6 of 36. And then since 36 can be expressed as 6 squared, we put the square out the front, which is 2, and log base 6 of 6 becomes 1. Because 6 to the power of 1 is 6, right? That's also a way to explain that. There's a variety of different ways you can approach this. Using the change of base rule, they do allow, oh yeah, I forgot to. Allowing the change of base rule, they do allow you to actually convert it to like a base of 4, which is actually very smart in this case. Because base of 4, right? Although in the marking guide, it goes straight to the answer, which is x equals 2 over 3. The reason why it does that is because 16 is 4 squared. So then using the same rule up here, 2 goes at the front, and then it's base 4 of 4, so it's just 1. 64 becomes 4 cubed, so it's just 3. Alternatively, rather than using that log law, if you forget it, it doesn't matter because these cancel out. You're dividing them. So it's 2 over 3. Here, what I did, I used the change of base rule, but I reversed it, and then I got back into this, right? Because the number in the brackets in the denominator becomes the base, and the number at the top in the brackets becomes what's inside the brackets. And since we can express 16 as 64 to the power of 2 over 3, then I put the power at the front, and then I just remove log base 64 of 64. So it becomes 2 over 3. The reason why this can be expressed as that is because I'll show you this. 4 squared is 16, right? Thing is, we want to express this as 64 to the power of something. And we know that we can demonstrate it by going 64 is 4 cubed, but then we want to how do I explain this? Um, okay, to get from this to this, we basically go this, right? That's a log law. So we have this number to the power, and then this number, which is 64, and then we do that to the power of 2 over 3. So then these actually multiply rather than adding. The powers multiply, so 3 multiplied by 2 over 3 becomes 2, which is 4 over 2. So this is the same as 16, so then I can express it like that. That was pretty difficult to explain for some reason. Yeah. So now we have another question. We convert this to a linear equation. So 5 to the power of 2, right? The base, and then this is the logarithm. So then 5 to the power of 2 equals what's inside the brackets. 5 squared, that's 1 mark. We're isolating x, we're rearranging for x. We minus 4 on both sides. So 5 squared goes to 25. We minus 4, 21, and then we divide by 2 to get rid of the coefficient, which is final mark. Okay. Button almost fell. Okay. Here, the solution just uses the log law and applies it onto 10, which, yeah, you could just do. But at first, I just rearranged the x's, the natural logs with x's in the brackets to be on the left side, and then ln of 10 to be on the right side. So I minus this both sides, and then I added this both sides. And then I used the log law, where since we're subtracting with logs of same base, we get this brackets, and then we divide it by what's in this brackets and combine it. Since they have the same base, so I've given the reason, bases are equal, we can equate what's inside the brackets. Yep, so that's 1 mark, right? Developing the linear equation, and then I multiply by x both sides, so then I get rid of the denominator, and then I just added x to get 11x, and then I divide by 11 to get 7 over 11 as x. Okay, so this is question where we're involving derivatives and integrating. So we're deriving and integrating. So to get acceleration from velocity, we derive velocity because acceleration is the rate of change of velocity. So one mark for actually demonstrating that we have to derive this. So this notation does demonstrate that. I did v prime of t. We're getting the derivative of velocity. Then, when you derive this, what happens? Okay, so 1 over pi is a constant. So the rate of change of constant is 0. So we ignore that. When we're deriving 3 sine t, we have the coefficient, the constant out the front. So 3, we leave it. When we're deriving sine, it turns into cos of t. And since there's nothing we need to do with the chain rule here, it's just sine of t. That's our answer. The displacement function. Okay, well, in this case, it's a bit more complicated. To get displacement, we're integrating v of t. So this does demonstrate that we're integrating, trying to find the area of the velocity, basically. Not really. But if you were to graph the velocity function, the area would be the displacement. Okay. Here, the constant is multiplied by t. It gains a t. Yeah. When we're integrating sine of t, so again, we leave 3 at the front. When we're integrating, we get negative cos. To double check that, when we derive this, we should get sine back. Negative cos t, so negative multiplied by negative sine t. Okay, which is exactly what we get. Negative, negative makes positive, so it's just sine t. And then we add c, because we don't know if it's shifted. We don't know the vertical shift, right? No matter what it's shifted by. Since it's a constant, using the same logic, when we derive it, the constant disappears, so we get the overall same velocity function. So we need to represent that using the constant. It's an indefinite integral, so we need to show that. So 1 mark for correct integration of the first term and 1 mark for correct integration of the second term. Then, given the context, at t equals pi over 3, the displacement is 4. We can sub that in to work out c. Yep, 4 equals, we sub it in, the pi's cancel, leaving us with 1 over 3, and then negative 3 cosine of pi over 3. I just added it on both sides, so it becomes positive here, and I've subtracted 1 over 3 on both sides to get negative a third here. 4 becomes 12 over 3 if you put it in as a fraction form with a denominator of 3. So then 12 minus 1 equals 11 over 3, right? 11. But then since the denominator is 3, it becomes 11 over 3. And then cosine of pi over 3 is a half. So then it's 3 over 2. And then we get a common denominator, so we multiply the top of this by 2 because we're trying to get 6 as a common denominator. It's the lowest common multiple between these two denominators. It's just multiplying them together. Then we're tripling this, so it becomes 9. So 22 plus 9 is 31. That's 31 over 6 as c. And that's our last mark. And then we can express it as the entire displacement function. Okay. Question 15. So I'll only show the marking scheme because you can see the question. So we're given a function, right? X squared e to the negative x plus 4. The second derivative is also given, so we can actually work that out just by deriving it ourselves, but they do happen to give it to us. Okay. I'm not going to read it out because, yeah, hopefully it's visible. And then we get graphs for each, which is excellent. Fabulous. First part is 2 moles. Determine the coordinates of the local maximum of f of x. So we need to know that local maximum means that the rate of change at that point is 0. And also the second derivative at that point is going to be negative, right? It's going to go up and it's decelerating, right? The rate of change is the rate of change of the rate of change. Or no, the rate of change is decreasing. So it's slowing down, right? I annotated the graph during my stream that ended. So I was just talking to myself. It slows down, right? The rate of change slows down until it halts. Halt. And then it stops and then goes down, right? So first I identified that the rate of change is going to be 0 at that point. And then since the first derivative is given, we can use that. So I sub that in. Yep. And then using our null factor theorem, we just make x equals 0 or 2 minus x equals 0 or e to the negative x plus 4 equals 0. Since if you multiply by 0 for one of these factors, the whole thing is going to be 0. X cannot be 0 just based on the graph. Yeah. So then I said, I rearranged for x for the second term, so x equals 2 in this case. Right? When we add x on both sides, it cancels out on the left side. So then this makes the most sense because it is in the positive part of the local max. This is a decaying exponential function. It can't actually reach 0. It can approach it, right? As you increase the value of x, it's going to get smaller and smaller and smaller because when you get a negative exponent, you're basically dividing it by the positive exponent, right? 1 over e to the x. Let's say you have e to the negative x, right? It's basically the same as saying 1 over e to the x. So then you're dividing it by greater and greater and greater numbers until it's like very, very small, but it's not going to be 0. So that's why I said this can't be 0. And this can't be 0 just based on the graph, right? It doesn't occur at 0. So x equals 2. We're asked for the coordinates. We need the y value. We sub x equals 2 into the original function, which is up here. So 2 squared multiplied by e to the negative 2 plus 4. So then this becomes a power of 2. So that's 4e squared. So then I wrote it as 2 comma 4e squared, which is how it's demonstrated in the formula sheet. Okay. Part B, pretty simple. It links back to what I was saying before. The second derivative is going to be less than 0. So I input x equals 2 into the second derivative, and I got negative e squared. Okay? And then since the second derivative is less than 0, it's local max. So that's all we basically need to do. Okay. Determine the x coordinates of any points of inflection. Okay, so in this case, we know inflection points occur when the second derivative is 0. So then I let the second derivative, which is this, it's given in the question, equals 0. Then again, we use the null factor theorem. So this quadratic factor equals 0, or this exponent part equals 0. But we said earlier that it can't be 0. Same reason, right? It's always going to be greater than 0. So it's going to be the solutions to this quadratic factor that are the x coordinates of points of inflection. We get the quadratic, we can use the quadratic formula for this, or we can use any other method that's perfectly valid. I just decided to use the quadratic formula. So then it's negative b plus minus square root of b squared minus 4ac over 2a. It's written here, just in case you have forgotten. So we sub in the values, right? A represents the coefficient of x squared. B represents the coefficient of x, C is the constant. We sub in the values, we simplify. Now, you might notice that they don't simplify, right? They just keep as this, right? 4 plus minus square root of 8 over 2, which is perfectly fine, but simplifying is pretty useful in this case, I guess. But in this case, I'm kind of contradicting myself because clearly it's unnecessary based on the marking guide, but it's always good to simplify in questions. Okay. Question D. Part D states, determine the intervals where the original function is concave up and concave down. We know that it's concave up when the second derivative is positive, and it's concave down in the opposite, right? When it's negative. When the second derivative is negative. Okay. So I said, given that the second derivative is this, ignore this, right? Because it's positive. So it doesn't have any like contribution to the sign of the second derivative, because when you multiply a positive number with any other number, the sign of the other number is just going to stay the same, right? So it doesn't change anything, right? And then I said as a, which is the coefficient of x squared, is greater than 0, it's a smiley face. Yeah, it's a smiley face. So it's going to look something like this union symbol, right? It's going to look like this in the graph. We know that there's two solutions, so this is fairly accurate. Except one of the solutions is not in the negative part. It's actually they're both positive solutions. Okay. In between the x-intercepts, they're going to be negative. The second derivative is going to be negative, right? It's going to be under the x-axis, right? The second derivative will be beneath the x-axis, hence negative. So if it's negative, it's going to be concave down. So that's why I said in between the solutions we got, right? So the solutions up here, the x-intercepts of the second derivative, in between them, they're going to be concave down. And then I said when it's greater than the more positive solution, the larger solution, and so it's going to be concave up when it's greater than the solution that's more to the right, which let's say it's here. When it's greater than that, it's positive, right? And then we also need to add, so the union, we need to include the other part. When x is less than the left solution, so it's going to be like this, it's concave up as well. Yeah. Okay, so that does relate to it. But the thing is, I didn't actually explicitly specify the relationship between concavity and second derivative. It's implied. But I think based on my statement here, right, it does demonstrate that. I think it does demonstrate some knowledge that if it's negative, then it's concave down because that's between. So I think that's valid. Okay. Question 16. So correctly determining A and B gradient of the tangent, equation of the tangent, and then just communication. So that's the marks associated. Okay. I'm going to zoom in to the sample response. Okay. Here you go. So the question states that determine the equation of the tangent to the function y equals x cubed plus ace x squared plus bx plus c at the point of inflection 1, 6. So we're given a point that lies on the function, and we're given some details on what the point actually represents. So it's not just any random point, it's actually a point of inflection on the cubic function. That's very important because in the question before, right, in the part C, state any x and the x values for the points of inflection, for any points of inflection. And we said our opening statement was that, at points of inflection, the second derivative is 0. Okay, so that's something we can use to work out A and B, the unknown coefficients. So I first stated the information in the thing, right? And then I said that the second derivative at x equals 1 must therefore be 0. Okay, so I derived it. I derived the function, so the first derivative becomes this, right? We're using the shortcut method, and then we're just deriving each term individually. 1 disappears because it's a constant. Bx is just b, And this 2, the power 2 goes to the front, and we subtract it, so it's 2ax. Same thing with this, so it's 3x squared. And then we derive this again. So then we get 6x plus 2a. We know that when we sub x equals 1, it's 0. Second derivative is 0, so then we can use that to work out a, which we got was a equals 3. Okay. They kind of don't include the working out, but in the answers, but what I do is I just sub in. We know that 0.16 lies on the function, so we can actually use that information to work out b. Since we know what a is, we only have one more variable to work out. We're given an equation, and x and y is known, right? 1, 6. So we can sub that point in, and then we can sub a value to work out b. So that's why y is 6 here, and then we sub in x equals 1, and then we work out b. We just rearrange everything to get b equals 7. So we've found the unknown coefficients. Okay, that's 2 marks. Then what we need to do is work out the equation of the tangent to the function at 1, 6. Okay. So I've written the function with values of a and b. Yeah. And then we get the first derivative. We want to know the first derivative at x equals 1, right? Which would be the gradient of the equation of the tangent. And then we work that out to be 4. So then the tangent equation would be something like y equals 4x plus c. We know that the tangent intersects the function at the inflection point. Okay. So then we can sub in 1, 6 because it's a common point for both the tangent function and the function, the cubic function given in the question. So then we can sub the point in to work out c, which we get is 2. So then the tangent becomes y equals 4x plus 2. Okay. So now, last mark was logical organization, which I believe I did. Okay. This one is interesting because it's similar to the previous question. We were determining A and B, but this time that's the entire question. So it's 7 marks. That shouldn't deter you from actually attempting the question. It's not an overly complicated question. It just involves a lot of information and our understanding on what our probability density functions have, like their characteristics. That is the key part to solving this question. Without that information, it's pretty difficult to actually complete this question because that's like the keystone to, understanding how to solve for A and B. So A and B, again, 2 variables. we're going to be involving simultaneous equations somewhere, right? We're going to be involving two equations that we equate, and then we sub in A or B into the other equation to work out the values. We're given it's a continuous random variable. It's on the formula sheet, right? We know that to find the mean or the e of x of a continuous random variable, we integrate with the bounds that are specified, which in this case is 0 and 1, and then we multiply x with the continuous random variable probability density function, right? Okay. First, what we can do, we need to recognize one of the characteristics. The area of the probability density function is 1 for the bounds, right? So from 0 to 1, this given function, the area of that will be 1. And that's 1 mark. So I've given my reasoning. So given f of x is a PDF, right? It's a probability density function. So then we can work out the probability density function like area. So we use the definite integral. A, we multiply it with x, we add an x, right? After it. And then in this case, we increase the power by 1 since we're integrating. And then we divide by the power, the new power. That's slightly different to derivative. It's kind of, it's basically the opposite. Yeah. So rather than like if we were to derive this, rather than multiplying the term with the power and then minusing 1 from the power, we first divide it by the power plus 1 and then add 1 to the power as well. Okay, I don't think I explained that well. Either way, we add 1 to the power, so it becomes x cubed, and then we divide by 3, which is the new power, obviously. And then we apply the bounds. So we sub in 1 first, so the upper bound. So x equals 1. So then it just goes to a multiplied by 1, which is a, and then plus b multiplied by 1 cubed, which is just b, and then that's over 3. And then this equals 1. The reason why there's no 0 part is because we can recognize that x is involved in both terms. So although for definite integrals, right, you're subbing in the lower bound, in this case, since it's 0, when you sub in the lower bound, you subtract it, right, and then you sub everything in, but given that it's subbing in 0, this goes to 0. So you're subtracting by 0, which doesn't change it. So then you can answer like a plus b over 3 equals 1. Now, the QCAA multiplied this equation by 3 to just get rid of the fraction, which is something you can completely do. That is fine. If you prefer to not work with fractions, that makes sense. It's completely okay. I did do that in my other part, right further down in the solution. So we're given that the expected value of x is 3 over 5. Okay, if we navigate to our formula sheet, or in this case, we can just look at the cycle response. So we get 1 mark for generating an equation in A and B, 1 mark for the definite integral, yeah, which we did. Okay, so we need to recognize that the expected value of a continuous random variable is just this. It's like, write it in green. So the bounds are infinity to negative infinity because it depends on what the probability density function specifies. We multiply x with p of x. So p of x represents the probability density function in this case. Yep, so that's it. So what you can see in the like where I'm pointing at, right down there, um you can see that the integral p of x, or the probability density function, is multiplied by x. So there's brackets around the probability density function, and you have you're integrating it. And since we're given that this equals 3 over 5, we can actually work this out. So I distribute x to both terms, so giving us ax plus bx cubed. And then the bounds are 1, 0, just like before. Then when we integrate it, we add 1 to the power, so ax squared, and then we divide by 2. So then ax squared over 2. And then same thing for here. We add 1 to the power, it's x to the power 4, but then we divide by 4. We get this. This equals 3 over 5. Again, we're solving in the same bounds, so 0 we can kind of omit. We can kind of ignore in this case. Do not do that in the exam if this is not 0. So do not get a habit. I think this is not good for me to do that. If, like, let's say you remember this, you remember what I say in like the exam. I highly doubt that, because like yeah, like, really, like, I'm not a teacher, and I'm pretty sure you know your teachers would probably say much more memorable or important things than me. Okay, so just make sure in an exam you recognize that when you sub in 0, it's going to go to 0 here. But when it's not 0, actually sub it in, right? This would become like, so when we're subbing it in for 1, we get this, which is just a over 2 plus b over 4. But then right after that, you'd subtract what you sub in for the lower bound. So a 0 squared over 2 plus b 0 to the power 4 over 4. And that's what you'd have. Let's say you're subbing in like a half, because a half is still less than 1, so it makes sense. Then you'd continue with the process, right? You'd actually continue the calculation. But in this case, you're subbing in 0, so it doesn't actually matter as much. Okay, here it goes to this equals this 3 over 5. We want to get rid of the fractions because they're messy. They have 3 different denominators. So what I found out was that, the lowest common factor, or no, lowest common multiplier would be 20. So I have to multiply 20 on both sides. 20 over 2 becomes 10, so it's 10a. 20 over 4 is 5, so it's 5b. 20 over 5 is 4, so it's 4 times 3, which is 12. And that's the final equation that we can use, which is this. Correctly generates the second equation in A and B. Okay. So as you can see from what's shown below, what's shown right here, yeah, so we've done that. Then we can sub in this. So I've rearranged for A. We can sub that in into this equation to work out what B is. We distribute 10, so 10 minus 10b over 3 plus b equals 12. We subtract 10 on both sides, so that's why I removed the 1, because it goes to 2. Then in this case, we multiply by 3 on both sides. So the right side goes to 6. This goes to 15b. This just cancels with the denominator, so then it's negative 10b. So it's 15 minus 10, which is 5, and then that's the coefficient of b. So then we divide by 5 to isolate b. So 6 over 5. Alright. Then we get an answer of 3 over 5 for a, because we sub that back into the original equation up here, right? I don't know if I should move my webcam. Is it like better? Like, is it more interactive? Is it more fun? I don't know. Okay. So that's it. And then the last mark is just logical organization. Yeah. Okay, second last question. Like this paper wasn't difficult. I went through it pretty quickly. It's just that I was streaming to no one to end it for some. So here, let me explain it. So I drew a diagram. I was like, oh, okay. Let's read the question actually. Determine the area of the largest rectangle that has one side on the x-axis and two vertices on the curve y equals e to the negative x squared. Express your answer in simplest form. The curve is sketched below, which is good. Basically, we want to find a rectangle, right? That's defined by this function, kind of like the two vertices are the two highest vertices are on the graph. So you basically make a rectangle based on this, and you want the largest rectangle area. Okay, so it's going to be somewhere like here. Okay, probably. The one mark for actually showing like demonstration that yeah provides evidence to support decision about dimensions. Yeah. Okay. So here's my reasoning. Why what I did. Okay. Let me move this out of the way slightly. So we know that actually I've kind of written my explanation. This looks symmetrical. Like just based on the graph, it looks symmetrical, and that's because it is. It is symmetrical about the y-axis. It's like it's mirrored from one side to the other, right? Okay. Because the power is a quadratic. So if you get a negative x value and a positive x value, the overall value is going to be positive. But in this case, since it has a coefficient of negative, it's going to be negative. No matter what x value, what real x value you put into this equation. So I've written, given that the function is symmetrical along the y-axis, I think that's the correct term, right? It's mirrored from the vertical axis, it's reflected on one side to the other. The total area of the rectangle can be formed from doubling the area of the part in quadrant 1. So Q1 represents quadrant 1, which is this part, right? The area of this is just half the total area of the rectangle, since the area of this is equal to the area of this. So the area of Q1, so the area in quadrant 1 is just base times height, which is x, right? It's defined, the base of the rectangle is defined as the x-axis. So the length or the base of the rectangle for quadrant 1 is just the x value. X goes from 0 to x. Yeah. And then it's multiplied by the height. And we know that the vertices, of the rectangle, the top ones, are defined by the function. So we can sub in y, which is e to the negative x squared. So then the area of Q1 equals x times e to the negative x squared. The total area, we stated that it's just double the area of quadrant 1, so we just put a 2 at the front, so it's 2x e to the negative x squared, which is actually what they got, exactly, which makes sense. Okay, we're trying to find the largest area, so this is like kind of like a optimization problem, I think, yeah. So maximum area, right, we want the local max, okay? So local max, it's when the derivative is 0, right? The rate of change is 0. It starts slowing down. So then when we derive this is the product rule. So let's let u equal 2x, and then v equals e to the negative x squared. Okay. The product rule involves u prime v plus u v prime. U prime in this case is just 2. When we derive 2x, we get 2. And then we just multiply by the exponent, the exponential part. So it's 2e to the negative x squared. Second part, we leave 2x, right? It's plus u v squared. So now we derive e to the negative x squared. That gives us a value of 2x multiplied by negative 2x, because that's the derivative of the exponent. And then we just leave the exponential part, because when we derive this, we get the same value. The derivative of e to the x is e to the x. That's a characteristic, and it's also in the formula shape. Okay. Now from here, I simplified. So I multiplied this with this to get a coefficient of negative 4x squared. Something to note, these terms share a common factor, e to the negative x squared. So after letting the derivative of the area equal 0, I factored that part out. So now we have 2 factors. And then because of that, we can use the null factor theorem. So then either this or this equals 0. This cannot equal 0, because it's going to be greater than 0 always, no matter what the value is. Because, like I said earlier, this is a decaying exponential function, but you know, the more negative the exponent becomes, the closer and closer it's going to become to 0. It's going to get closer to 0, but it's not going to be 0. So this can't be a solution. Therefore, we look at the solutions of this. So we add 4x squared on both sides, then we divide by 4. So then we get x squared equals a half, and then we square root both sides, making sure to plus minus the other side, because it could be positive or negative. When we square this, then the negative just disappears, right? Negative 1 times negative 1 is 1. So then it's plus minus square root of 1 over 2. We accept the positive solution. Now, I forgot to scroll down. The reason QCAA provides is different from my reasoning. Like QCAA just used like the definition of local maps, kind of. They didn't actually work out the second derivative, because you're just using the product rule again. And it could be a bit time consuming, because this is the second last question, right, on the paper. So you might not have as much time if you're going in chronological order with the questions. However, my reasoning was slightly different because of what I defined. So I said x equals positive. So I accepted the positive solution and I rejected the negative solution, because x must be greater than 0. The base length cannot be negative. So I've already defined that x is the base. Also, this links to the area, because if x is negative here, right, if we let's say this is, okay, let's say we said negative, the negative solution was correct, and we subbed it in the area function. We know that e to the negative x squared is positive. It's not going to change the sign, right? It's not going to contribute to it. By subbing in a negative x value here, we're going to make this entire thing negative. Area can't be negative, so it's invalid. So that also ties into that. So this probably is a valid reason. Okay. So then now we have the x value at which the rectangle is a maximum. Since we have that, we can sub it in back into the formula, right? So then it becomes 2 multiplied by square root of 1 over 2 times e to the negative a half. Because we worked out earlier, x squared is just 1/2. So I just solved that in. But either way, you know, when you square the square root, they just cancel. So it's going to be the same either way. Okay. 2 multiplied by the square root of 1 over 2. This is interesting because it actually becomes square root of 2 over 2. I mean, no, square root of 2 over something. Or in this case, since e is to the power of negative half, that's basically the same as 1 over e to the power of a half. And e to the power of a half is square root of e. So it's 1 over e square root of e. That's why square root of e is in the denominator. So I'll explain this part a bit more. The 2 multiplied by square root of 1 over 2. Okay. So it's basically you're square rooting the top and the bottom. So square root of 1 is 1. Square root of 2 is this. We can multiply it by a variant of 1, which is just square root of 2 over square root of 2. Right? We're just multiplying by 1. We're not changing the value or anything. This becomes 2, right? This is essentially the same as squaring square root of 2, which then cancels the square root and the square. Since it's 2 over 2, we can cancel that out, so it leaves us with square root of 2. So it's square root over 2, square root of 2 over square root of e, which I just combined. Units squared, which is the given answer, as you can see. So I did show logical communication and organization. This question is great. When I was streaming this question, but I wasn't streaming technically. I thought when I thought I was streaming this question when I was going through it, it did challenge me quite a bit. It was excellent. Yeah, this question is good. It's quite simplistic in nature, right? The chair's pretty squeaky, but okay. This is a very simplistic question, but it's excellent. It has a lot of good components. I'd say this is a good test of your knowledge. Okay. Determine the equation, so this is the question, determine the equation of the tangent to the curve y equals x ln of x. It passes through the point 0, negative e. Yeah? Passes through to this point. Okay, so this point is common in both the tangent and the function. That's something we need to consider. Okay, first, how do we find the gradient of a tangent in any case? Okay, we find the derivative of the curve and then we work out the derivative, at the point of intersection. This is where things get interesting. You might think, oh, the derivative at x equals 0, but you might soon realize that you can't even sub this value in. Okay, let's first inspect y. When we derive this, we're dealing with the product rule. We're dealing with two functions multiplied together, which is x and ln of x. So I let u equal x and then v equal ln of x. So it's u prime v plus uv prime. I've written it here. Yeah. So the first term goes to 1 times ln of x because the derivative of x is just 1. Then it's u v prime, so u just stays here. V prime, so ln of x derives to make 1 over x. So then it's x over x, which is just 1. So that's the derivative function. But you might be thinking, oh, now we sub this point in to find the derivative of the tangent. It's not that simple. It says, determine the equation of the tangent to the curve that passes through the point 0, negative e. It doesn't say at 0, negative e. It doesn't say this point is a point. Oh, wait, yeah. This point I said earlier that this point is common for the tangent and the function, but that's actually not true. This point, the tangent passes through this point. That's what it's saying. This point does not actually occur on this function. If you sub in 0, so x equals 0, this goes to 0. The first part goes to 0. ln of 0 is an asymptote. It's not possible. So this is actually not a point on this function, on this curve. Yeah. So that's something interesting. So what I did was I realized, oh, wait, so the derivative just equals this. Right? The gradient of the tangent equals this, and it's at some x value on this curve. So then I differentiated the x values and y values for the tangent and the curve. So the curve was 1, I made it have a subscript of 1, the variables. So then the derivative, the gradient of the tangent just equals this. So x1 represents a constant, not a variable in this case. So then the equation of the tangent looks like this, yeah? And then it's y equals mx plus c, but in this case, m is this. I was like, oh, okay, we have a point that the tangent passes through, so I can use that to work out c. Because 0, subbing in x equals 0, cancels this out. So that's good. Right? We don't have two variables to work with, so we can work out c at least. So this goes to 0, so then c just equals y, because, you know, it's the y-intercept. So it's negative e. So then I subbed c into the linear equation that we determined for tangent. So it becomes this. Now, we need to work out this x value, because the whole point of this is determining the equation of the tangent. Okay, I made a mistake here. This was actually kind of correct. I just didn't, this was correct, but I didn't, consider it. Okay, let's read the sample. The point of tangency, so they used subscript zeros. So at x equal x0, y, ln of x0, which is the y value of the curve, the equation of the tangent passing through the point. They've worked out the tangent, which is this basically. Substituting the points, the coordinates of the point of tangency into the curve. See, this looks very simple because I think I've already been getting it. But I did get it in the end. I used a slightly different method. This is the same to what they did, right? We know that the initial point that we don't know passes through both the curve and the tangent. What I just didn't recognize is that we've already kind of said that x1 is a constant. We know that it's a point. So I can sub in x1, you know, to get the coordinate, and then, you know, the y value, this, is going to equal this, which I did, but I was like, this represents x for this, and then this represents x for the tangent, right? That we need to differentiate the distinguish the x values. But no, the x value we sub in is the same to get the same y value. That's the mistake I made. So in this case, like we did in the sample response, I should have just made every x value the subscript of 1 because we're subbing in this constant and then we get the same y value. But I failed to do that, so then I treated the x's like they're different variables. For example, here, if you treat it as the same variable, look what happens. x1 ln of x1 minus, when we distribute x1, we get negative x1 ln of x1. This term is the same as this term, but we're subtracting the same terms together so they cancel out. Then we get negative x1 plus 1. So that's just negative x. So negative x1 multiplied by plus 1. We get negative x1 equals negative e, which in this case goes to e. So negative x1 equals e. Then we can sub that in, and then what do we get? ln of e is just 1, so 1 plus 1 is just 2, so 2x minus e, that's the equation, which is actually the answer. So very simple, right? I just made a mistake in actually distinguishing the terms, because they're actually the same, right? If you just sum them the same value for the x, you get the same y value, which I did state, but yeah. So instead, because this wasn't working, right, I didn't know what to do here. Instead, what I chose to do was something different. We know that there's some point x1, y1 that's common, or x1, y1 that intersects. So I used the gradient I found out, and then I used just the rise over run formula that we learned in like grade 7 and something, I don't know. So then this point, right, is common for the tangent. So then y1 minus the other point, which we know is given, right, that the tangent intersects through. So then in terms of 0, it's just subtracting 0, so there's nothing there. In this case, for some reason, I realized that, oh, you can actually sub in x1 ln of x1. So this is basically the same outcome as this. Yeah. For y1, I subbed in this. And then I multiplied by x1 on both sides, and that's why there's x1 for both terms. This and this are equivalent, so I cancelled them out, giving x1 equals e. And I subbed that in, simplified, and I got that. Yeah, so that was it wasn't a difficult question, but it definitely involved some understanding of, a decent understanding of like your knowledge on tangents and, you know, well, just mainly the characteristics of tangents, yeah. Okay, so that's paper 1 covered, the sample, for the sample methods paper. I'll record a video soon after for paper 2, but in this time, paper 2, I'll actually be going through the questions during the video. Something to note is I have already covered the multiple choice questions for paper 2 because I didn't realize that footage wasn't working. So yeah, that was pretty unfortunate. Okay, so here's the marking guide. I forgot to show it. Yep. There we go. Okay. I'll see you in a bit, I suppose. Yeah.